Hello to everyone. Today I'll be discussing that the intensity distribution absorption band from Frank-Condon Principle. And before my last class, I have discussed about the intensity distribution for the couple of the molecules, how these intensities are varying for the different energy levels, for the different vibrational energy levels. Uh, So, as there is a requirement for the electronic transition that there should not be change in an internuclear distance. So, the transition is taking place for the vertical line. Now, and this observation spectra and all the observations are taking place that the progression in the new prime is initiated from the new double prime is equal to 0. So in a figure A, B and C, these are the absorption spectra intensities for this O2 molecule, CO molecule and the I2 molecule. So in a figure 1, figure A, the internuclear distance are almost equal in the both the electronic states, in the ground state and the excited state. In a B, this internuclear distance for the excited state is slightly greater than to the internuclear distance for the lower energy state. However, the internuclear distance for the excited state for the I2 molecule is very much larger as compared to internuclear distance for the ground state. All the transitions, that is absorption, starts from the lowest level, this new double prime is equal to 0 level for the ground electronic state. In figure A, this is figure A, this is A, this is B and this is C. So the transition is new double prime 0 to new prime is equal to 0 is most probable because it connects the configuration of high probability and also appears as a vertical line as required by the Frank-Condon principle. R does not change. That is Frank-Condon. The requirement is that R does not change during the electronic transition. The transition is levels. If you look at this most probable is this new prime double prime is equal to 0 to new prime is equal to 0 because their distances are almost the same. Corresponding to, there are progressions corresponding to new prime is equal to 1, 2, 3 and so on, but they are involved change in R because once obviously the R will be changing for them, so their transition, these lines are not very much intense as this R is changing because in the case of because every progression, every transition is taking place, absorption from new double prime is equal to 0. Now it is lying with this R is new prime is equal to 0, it is lying vertical one. And once we are going for the higher states, because this violates from the Frank-Condon principle, the reason is that this R is changing, this RE prime and RE double prime are changing. So these lines are, the intensity is slightly decreasing. So if you look at in this case, now at the 0-0 transition, the line is very sharp, very intense one, and gradually it is decreasing. So in figure B, the most favored transition is, this is new double prime to 0 to new prime is equal to 0, and here new prime is equal to 0 to new prime is equal to 2, which connects that the configuration that the maximum probability and also satisfy the Frank-Condon principle, that is the vertical axis is matching with this distance is matching with this vibrational level. The transformations corresponding to level new is equal to new prime is equal to 0, 1 and 3, 4 and so on are also taking place, but as these are, because the changing of this new of this RE is changing, so their intensities are comparatively less. And if you look at for the 0-0 intensity is less and then slightly greater, then this for the 2-0 is the maximum one, and then gradually again it is decreasing. And this is a distribution of the is observed for the absorption band system of carbon monoxide. In a last case for the I2 molecule, the vertical electronic transition from the midpoint nu prime is equal to nu double prime is equal to 0 level is most likely to terminate. It's a continuum of the upper electronic state, this dissociating the molecule. So if you look at, this is matching with this almost dissociating energies. So that is why the transitions are taking place for these energies levels, but because this R is changing, the internuclear distances are changing, so it is violating that the slightly that the Frank-Condon principle, then the intensities are very small. And if you look at almost at the dissociation energies or the continuum, we are getting the maximum intensities. This is corresponding to I2 molecule. If you remember, we have done this for the we have done it for the our I2 molecule in the previous class. So this is the how the intensity distribution in absorption band, and the same thing will be explaining for a emission band as well. I think it's now last topic of this molecular spectroscopy, and here I will be discussing that the intensity distribution in emission band, or that is the Condon parabola. So far I was discussing that the Frank-Condon principle, that for the absorption band. Now, according to the Frank-Condon principle, the distribution of intensity in a band progression with nu prime is equal to 0 in emission corresponds exactly the same way that the progression with a nu double prime is equal to 0 in an absorption. There is intensity maxima at nu double prime values depending on the relative position of the minima of the total potential curve. So the greater the difference, so we'll see that the greater the difference of this R E of this R of E double prime, the larger the value of nu double prime of the intensity maximum. So once I have the larger the difference, so we'll be having that the intensity maxima will be taking place for the nu double prime, that is higher level of this lower energy states. So we'll see that, as I said, that for the absorption spectra, the progression and for the emission progression are the same for the nu prime is equal to 0 and the nu double prime is equal to 0. So in emission, however, the initial level is, in the emission 1, at the initial level this nu prime is equal to 0, or nu prime are sufficiently well populated. It means that we may have the progression from this nu prime to the all the lower energy states of vibrational state of this electronic state from the each level of this vibrational level of the excited state. On the other hand, in a case of the absorption, you have the progression all are initiated from the nu double prime is equal to 0 to the all of the above level. In this case, we have a sufficient, that depending on how much is the excitation, then if the excitation is sufficiently large populated all the vibrational levels, then from the each one we are getting the progressions. So hence the number of the progressions are seen in our emission spectra. The intensity distribution for the band progression in emission with. So now the band progression for the emission spectra greater than nu prime is equal to 0 are entirely different as compared to my absorption spectra. Like in an absorption spectra, nu prime is equal to 0. So now if nu prime is equal to above to 0, then these progressions are entirely different as compared to the progression or the as compared to the progression are initiating from the nu prime equal to 0. So in order to understand this situation, how it is happening, that suppose let us have this transition, this electronic, this is a energy potential diagram for this electronic states. Suppose now in this case you have an excited level, this A and B, suppose, then as we know that the molecule, these atoms are staying for a longer time at these turning points. So, according to the Frank-Condon principle, there must be a transition in a vertical line. Then you have a possibility to maximum probability to transition from A to F and B to C. So now you have two vibrational states. For a lower energy state, this F or E of F and C of D. So you have a two excited state. Now once I'm saying that this, you have a maximum probability to be atom at this position at the turning point A and B. You have a maximum probability either A to F or B to C. It means that you have a two new states, vibrational states C, D and E, F, and you have the two maximums. And if the value of this level nu prime is increasing, and this point C is sharply, very fast it is moving. So it means that the state will be somewhere here. For the another level, you will be getting that somewhere here. So the separation will be increasing as we are increasing at the level of nu prime for the higher one. Then the C, this point will be higher. It means that you are getting the two intensity, two maximas, and the separation is increasing as you are going for the higher levels. So we can plot, now we can plot that if the progression is from nu prime equal to 0 to 0, then you have only the one intensity maximum. However, once you are going for the above one, then you have the separation is increasing. So the intensity distribution, their distribution we can plot in this fashion, that this axis is representing nu double prime and nu prime. This is nu prime. It is a 0, the 0, 0, then only the one intensity maximum, that it is just a vertical line. And once you are moving for the either is this side or this side, then you have the separation. So this is called the Condon parabola. So this is the array, this nu prime of nu prime and this is nu double prime. This array similar to that, how this diagonally I have plotted. These are the diagonally plotted that where this delta nu is equal to 0 means from the 0 to 0, 1 to 1, 2 to 2, 3 to 3. However, once you have asymmetric plus minus 1, plus minus 2, plus minus 3, you have these maxima are the both the side. And this is just plotted from the, if you remember that Dislandre table, from there itself we can plot this. And this parabola represents the distribution characteristic of reduced with this phenomenon, this exploration. There are two intensity maxima in all the horizontal rows. So once you are moving that in the horizontal rows, corresponding one, this is we have the two maximas. These are the maximas. And except that nu prime is equal to 0, which has only one maxima, as we move for the higher nu prime values, there are two maxima, two limbs of the parabola, two limbs of this parabola. So in the case concluded in this figure, a given progression, this nu prime is equal to 0 constant. This suppose for this expression, if this nu prime is equal to constant, the separation of two intensity maxima are therefore width of the Condon parabola increase with increasing the r. So if I am putting that this nu prime is equal to constant, then the separation will be decided by the separation between this r of E prime and the r of E double prime. The separation of this will be deciding that how much the separation of these intensity maxima are there. So that is why the Condon parabola, for example, for the another molecules that while plotting that the Condon parabola, for some cases we will be getting these limbs are very narrow. For the other hand, for some of the molecules are very wide. That depending on the separation between these. Now, so this is now again this nu prime, double prime, nu prime. This is nu double prime, nu prime. This is nu double prime, nu prime, and this is nu double prime, mu prime. So this is dysplenary diagonal. Now for the molecule SIN, so we'll be getting that very small limbs like that. For the, this is C2 and this is for CO, and this you have this O2 positive. Now for the case of the Condon parabola SIN, that is for O2 positive, is must open, have the limbs almost right angle to the each one. So let us discuss it now. In the case of this one, SIN, you have this RE is approximately equal to this RE double prime, where the maxima is each progression, nu prime is equal to constant, coincide at delta nu is equal to 0. This is the diagonal sequence, that is delta nu is equal to 0. And whereas on the other hand, you have delta nu is equal to plus minus 1, you have this both the limbs. And these limbs are very narrow, they are not sufficiently very intense one, because their separation is very small, because this RE is equal to RE. Because in the case of this potential for the ground state and the excited state, this separation is small. That is why you are getting very narrow limbs of this parabola. On the other hand, like in the case of the C2 and CO, the delta nu is equal to 0, appearing this again, this delta nu is equal to 0, this is a diagonal, dysplenary diagonals. While the neighboring of this delta nu is equal to plus minus 1, plus minus 2, and larger number of bands are detectable, because the separation, larger band of the are detectable, and these are obviously not symmetric, because the reason is that once I was plotting that in the previous figure that A to E, and I was showing that this A to F and B to C, that is why these limbs are not very symmetrical, depending on how this potential is. Because as for the higher level of this R, this once we are going for the higher value of the R, the asymmetry is increasing in the potential. So as compared to the C2 and the CO, you have a wider limbs in this case of the CO. For O2 molecule, this is for the O2, this is R, the reference of RE prime and RE double prime is very large, apparent large, so contemporary is much widened, that the two limbs follow the nu prime, and this follow this nu prime progression and nu double prime progression. Because this both the progression, what does it mean? That once you have this excited energy levels, nu prime have 0, 1, 2, 3, and so on. From the each level, you have these kind of the emission spectra. That is why you are getting both the progression. So now to generalize it, now in the generalizing on this concept, that the intensity distribution in all the cases, that the potential curve becomes increasingly asymmetric with increasing the R. It means that nuclei spend more time in the phase of this R is greater than this R greater than this RE. Then the contracted phase as compared to this R less than to RE. So what does it mean? That the potential curve becomes increasingly asymmetrical with increasing the R. It means that the nuclei spend more time in this case, in this fashion, that it's an extended form where this R is greater than RE as compared to this contracted form, this R is less than to this RE. So according to the Frank-Condon principle, the transition will be more probable from one side from the other. So it means that the transition will be more probable in one side. Once I was showing that the asymmetric case, so once you have this kind of condition, that you will be getting that these transitions are probable from the one side itself. As I said, that at the turning points, these atoms retaining for the longer time. So once this is the case, not the expanded case, then it means that from the one end it has having the maximum probability. So therefore the system degraded to the red. So if this R prime is greater than this R double prime, the limbs of the Condon parabola will be stronger. Right limb. This is in this case, if R is greater than this R prime double prime, which is usual, it means that the right limb of the Condon parabola will be stronger, whereas for the system degraded to the violet, once this R prime is less than to R double prime, means the transition, because this R is less, you are going for this side, you are coming in this side, you are the violet. The system is violet, the left limb will be stronger. The left will be stronger. So thus we can obtain many information about the molecule from the study of the Condon parabola. So now this is the intensity distribution and emission band of the Condon parabola. Now everything is depending on this, how these limbs are stronger, this RE and this separation. And for, as I said, that this is increasingly very high. In that case, you have a maximum probability from the one end of that position contact. This is expanded or the contractor. Once the expanded one, then you have a red shifted one, a red contact, that is red one will be the right one will be the much stronger. And on the other hand, for the less than, if the average, if this length, internuclear distance is less than to that average one, in that case you have this violet, that is the left limb will be the stronger one. So this is all about the Frank-Condon principle, quantum mechanical and emission band and the absorption band. Everything we have discussed. And now this is the last class of our molecular spectroscopy. And I have covered almost each and everything, and the sum of the, I supposed to do as well some of the numericals, but I haven't. Now it's your turn to go through all these lectures and try to crack some of the numericals and some of the examples which are solved in your textbooks itself, and then we'll see. If you people have any problem, then you just can write in the Google class, then I will clarify as compared with respect to my videos, and you can mention the timing of the videos accordingly. At that particular point I will be emphasizing the things. So now I'm closing here now this semester paper of this molecular spectroscopy. I hope you have learned many things from this molecular spectroscopy and you will be performing better in your examination. And thank you, and I wish you all the best.